Okay, 5.4 practice number 1. When a polling company calls a telephone number at random, there is a 9% chance the person is going to pick up and they'll talk to them, and the survey is completed. Suppose a random digit dialer they do 15 calls. X is the number of calls that result in a completed survey. Okay, calculate and interpret the mean. Okay, so I do know it's binomial because it's either they pick up or they don't. Remember bins, right? Either they pick up or they don't. One call is independent of the other. One doesn't affect the other one. There's a set number of trials. There's 15. And the success rate is 9% every time. So the mean is, remember, if it's binomial, we can use n times p, which is 15 times 9%. Okay, and if I multiply those together, I get 1.35. Okay, so interpret this. If I call many people, we would get an average 1.35 out of 15 people. Okay. Part B, calculate and interpret the standard deviation. Okay, for the standard deviation, remember that's how spread out it is. We can use, since it's binomial, n times p times 1 minus p. So in this case, it's n, which we said was 15 people, p, which was 9%, and then you could write out 1 minus p, or you could say that's also 91%, right? 1 minus 9% is 91%. So if we work that out, we get an answer of 1.11 basically. Okay, the number of callers, successful callers, will vary by 1.11 from the mean of 1.35. Okay, number of successful callers will vary by the standard deviation from the mean by about that much. Number 2 says he drives the same route to work on Monday through Friday. The route includes 1 traffic light, and it's a 55% chance that it will be red when he arrives at the intersection, so a little over half the time. At a randomly selected workday, suppose we choose 10 of his workdays. X is the number of times he gets a red light. So if he goes through that 10 times, on average, I can use n times p. Okay, on average, he's going through the light 10 times, and the probability is 55%. So 10 times 0.5, it's 5.5, right? Because it's multiplied by 10 anyway. I went to my calculator anyway. So it means that on average, if going 10 days, 5.5 will be red. Okay, so on average, okay, 5.5 of them will be red. Okay, the standard deviation of it, square root of n times p times 1 minus p. So we have the square root of n, which is 10 times going through. Probability was 55% yes, and 1 minus that would be 45%, would be no. So square root of 10 times 0.55 times 0.45, or 1 minus 55, gives us 1.57. Okay, so what does that mean? Okay, the number of red lights will typically differ from the mean by 1.57 red lights. Okay, so we'll average this, but it'll differ by about that much from day to day. Okay, question number 3, we're dealing with the same red light problem. If the light is red on 7 of the 10 days, is that unusual? Okay, so we want to compute this, okay, the probability that x is greater than or equal to 7. Now we expected 5.5, right? That was kind of what we expected on average, but is 7 or more unusual? Okay, so we're going to go to Desmos for this. So remember, if you go to Desmos and pull up the thing on the bottom, the functions, go to distribution, a binomial distribution, okay, where our trials is 10, comma, 0.55. Remember to hit the find cumulative probability, and we want to find it from 0, so no, greater than 7, or equal to 7, from 7 through the max of 10. And we get a probability of 0.266. So that's not that unusual. So it is not that unusual to get 7 or more red lights. Alright, since it's not that unusual, we don't really have evidence to say that they're 55, if they say 55% of them are red, we don't really have evidence to say it's not. Okay. Next problem is baby elk here. So biologists estimate the randomly selected elk has a 44% chance of surviving to adulthood. Assume that an estimate is correct. They choose 7 baby elk at random. X is the number who survived to adulthood, and then we give you this, gives this distribution. So we could have 0 survive, or 1 survive, or 2 survive, or 3 survive, etc., all the way up through all 7 of them surviving. Okay, so we want to find the probability that fewer than 3 elk survive. So less than 3, not including the 3, but just less than the 3. So fewer than 3 would be the probability of 0 plus the probability of 1 plus the probability of 2. So if we put 0, 1, 7, 3 and the 1, 0.0950 plus the 2, 0.2239. Let me add that all together. Adding that all together gives me 0.3362. Okay, so there's a probability fewer than 3. There's about a third chance, right? 33.6, a little bit over a third of a chance that fewer than 3 of the elk babies will live. Okay, number 5 in your homework. Okay, special promotion for its 20-ounce bottles of soda. Some of them, the caps say, please try again, while others say, you're a winner. The company says 1 in 6 will win, so there's our probability. 1 in 6 people will win. Suppose they're telling the truth, that everybody has a 1 in 6 chance. 7 friends buy a bottle at the store. Let X be the number who win. Okay, so our trials, number of trials, we have 7 people that are doing the trial, right? So we could have 0 winners all the way up through all 7 people winning. And here's that probability distribution. Okay? The store clerk is surprised when 3 of the friends win a surprise. Are they just lucky, or is the company's 1 in 6 claim inaccurate? Find the probability at least 3 of the 7 friends. Okay? So we're going to find the probability that X is at least 3, so 3 or more. Okay, probability of 3 or more win. So once again, we can go to Desmos, binomial distribution, trials, there's 7 people. The probability is 1 out of 6 people win. And we want to know greater than or equal to 3. So our minimum is 3 and a max of 7. Okay, so the probability is 0.096. Okay, so 0.096 when you use the binomial distribution there, and you add those together. Okay, so if we answer all the questions here, is this enough to say that 1 in 6 is inaccurate? Nope. 1 in 6 is possible, is feasible. Okay, this is very possible. About 10% of the time I would have 3 out of 7 people, so that's okay. So yeah, we found their answer there. Next problem. Last one here. Thousands of travelers pass through the airport of Guadalajara, Mexico each day. Mexican customs agents want to be sure that passengers do not bring illegal items, but do not have time to search every passenger's luggage. Instead, they require each person to press a little button. It's either going to be red or green. If it's red, they get searched. Green means they go ahead. Okay, they claim that 30% of the people get a red and have to be searched. We're going to assume that's true. We're going to watch 20 people, so there's our N. N is 20, right? Go through. R is the number who get a red light. So, part A asks us to find the mean of R. So on average, how many people would get that red light to get searched? So you know it's N times P. So N, we know we're looking at 20 people, and the probability of them getting searched is 30%. Okay, so 20 times 0.3 gives you 6. So out of 20 people, we would expect 6 people. Okay, the standard deviation of R, square root of N times P times 1 minus P, which is the square root of 20 times 30%, and 1 minus 30% would be 70%. So, multiplying that out gives me 2.05. So we would expect it to differ from this by about 2 people. Okay. Part B says suppose that only 3 of the passengers got a red light. Okay, so we expect 6, but only 3 got that red light. Does it give evidence that it's really not 30%? Okay, maybe it's less than 30%. Okay, so we're going to find the probability that x is less than or equal to 3. Okay, find the probability that at most 3 people, right? So 3 or less than or equal to 3. So using Desmos, okay, binomial distribution. Okay, the number of trials, there's 20 people coming through, comma, and they claim it's 30%, so 0.30, 0.3, and the minimum, we want to know from 0 through 3. 0 up through 3. Gives you a probability of 0.107. Okay, so there's not enough evidence that their claim of 0.30 is incorrect. Okay, so we expect 6 people. Okay, if we get 3, that could happen 10%, almost 11% of the time, so not really enough evidence. Now, if I only get 1 person coming through, that would be very unlikely to happen. That might give you enough evidence to say that 30 people would not, that 30% is not accurate. Okay, come to class with questions for me.